This is a problem from your book. We have here a whole bunch of Toyota Corollas, used Toyota Corollas, and the price that they're selling for. First thing we want to do is decide who's the explanatory variable and who's the response. We have to make that decision. Do we think age would explain the price, or do we think price would explain the age? Now remember, correlation does not imply causation. We're not saying we're sure, we're just saying which one is more likely. And it's age should explain the price. You tell me the age of a car, that should determine or explain the price, not the other way around. You beat up a car and lower the price, that's not going to suddenly age it. Anytime time is one of your variables, it will be your x. Okay, so we need to make a scatter plot. So we define our variables. X will be our age in years, our explanatory variable. Y will be our price in dollars, our response. And we just draw out literally just plot points. That's all we did here. And we need to look at that for these reasons up here. Before we just start typing numbers into the calculator, we need to look and see, do we see a pattern? Is it linear? Are there outliers? So yeah, that looks like a nice linear pattern to me. Looks like it's going down. We have some kind of, I would say, strong negative correlation there. As age is increasing, prices are going down. I don't see any clear outliers. I don't have a data point way over here. Looks good. We're allowed to move on. If we don't like this picture, we stop and we just move on to the next problem. Okay, now we want to find the line of best fit. So I'm going to teach you next class how to do this in Microsoft Excel or your favorite spreadsheet program. Right now, I'm going to show you how to do it on your calculator. So the first thing you have to do on your calculator, there's a problem with your graphing calculator that we have to fix. We have to go here into catalog. See how it's blue and it's above 0? So we have to go second, catalog. Scroll down until we find diagnostic on. You got to scroll for a while. That one, diagnostic on, hit enter twice until it says done. Now you'll never have to do that again unless you change your batteries in your calculator. That's a do it once kind of issue. Now we fix the calculator. Okay, now we're going to type in all of our data, our ages and our prices. So we're going to go here into stat, into edit. We're going to type the ages into L1 and the prices into L2. Order doesn't matter as long as you make sure your points line up. Like this 8 better go with that 9998. They better be beside each other. But if you accidentally skip one, they don't have to go in this order. So type all the X's into L1, all the Y's into L2. Notice that they end on the same line. If one list is longer than the other, you've done goofed. Once you get everything in there, you're going to go here to stat, over to calculate, and down to number 8, linear regression. I know number 4 says linear regression also, and literally either one will work, but your book uses 8, and I want to be consistent with your book. So we're going to use number 8, linear regression. And then it's asking me, where are your numbers? Where's your X? I type those in L1. That should be the default. That should automatically pop up. If not, if that doesn't say L1, you grab it right there. You do blue or second, number 1. And then Y list L2. Go down and hit calculate, and that will spit out everything we need. Now, we got to be careful here. Think about lines. Think Y equals mx plus b. M is the one that sits by x. So look here, which one is sitting by the x? What they called b. I wish they didn't do that, but because, you know, we kind of have in our head that b is the y-inter. We just have to pay attention here. So my slope is this number, negative 844. The y-intercept will be the point 0.017673. There's my r. Notice we said a minute ago it was negative correlation. We even said negative strong, and look at that r, negative 0.86-ish. And there's the r squared that we'll use in a minute. Okay, so once we got all that, here's our model. Our predicted y value is this formula. So let's interpret all this. The slope. Slope is change in y per change in x. So for each additional x, y will change by that amount. And remember, it's units of y per unit of x. What was y measured in? Dollars. I know that because I wrote it down. That's a necessary step. Writing this stuff down is necessary. It's required. So my slope will be in dollars per year, y per x. So the model predicts, we're going to start every sentence with that. The model predicts that Corollas lose $844 in value per year. Okay, the y-intercept. Remember, y-intercepts are points, not numbers. So we get this value when x equals 0. What's it mean, x equals 0? What's a car that's 0 years old? We have a name for that. A car that's 0 years old. We call that a new car. So we would say here, the model predicts a new Corolla is worth that value. Problem is, that's not realistic. Used cars, this is a pretty accurate model. Used cars lose about the same amount each year, except for the first year. Anybody that's ever bought a new car, you know literally the moment you drive it off the lot, you just lost thousands of dollars in value. The moment you drive it off the lot. So in reality, we would not be linear in that first year. There would be a big drop and then it would go down. But that's okay. We just won't use this model to make predictions about new cars. That's not what it's built for. Our y-intercept a lot of times is going to be something silly. There's a problem we do later that predicts that the value of a diamond with 0 carats is negative some number. Imagine you go to the pawn shop or a jewelry store and you say, give me a diamond ring with 0 diamonds. And they say, sure, that'll cost you negative $50. Of course, it doesn't make any sense. But so what? We don't care about that. We only care about values in a certain range. These models that we're building are not meant to work forever. So we have to come up with what we think is a reasonable domain. So remember, domain from college algebra is the set of x values you're allowed to use. What kind of cars would make sense here? Well, we can't have negative x values, so we'd need our x's to be positive. And how far will this model keep working? I mean, can you imagine a Corolla 4,000 years old? It doesn't even make sense. These models only are built to go a little bit further than we already have. Our data here was from like 1 to 9. So we can make predictions a little bit outside of that range of values. So I said here, X's are probably between 0 and 20. I mean, once you get to 30 years old, your car becomes a classic and starts going up in value instead of down, right? Once it becomes an antique. I don't know what the year is for antique, but at some point your price will go back up. What about a range? What Y values make sense? What's the worst possible Corolla? If you got a car sitting on blocks in your front yard that's all rusted out, a junkyard will give you a couple $100 for it. So negative prices don't make any sense. So a reasonable range here might be from, say, $500 to $18,000. And we don't necessarily have to write this stuff down, but we do need to think about what X's make sense, what Y's make sense. Okay, our correlation coefficient, the calculator gave it to us. It was right here. Oh, that's a typo right there. Notice that. I hadn't noticed that before. That should say negative 0.86. And then I wrote here strong positive. I need to fix this document. I'm going to go back, edit this, and fix this. That should say negative. There is a strong negative correlation. Negative because it's a negative number. Strong because it's close to -1. Okay, this guy here, R squared. This is the same sentence every single time. You're going to have questions on this about your homework, questions on this about, or like this about, or on the test. It's the same sentence. You turn this into a percentage, that's about 75%. And then the sentence that you write every time is that percent of the variability in your Y units is accounted for by the model. Like, look at this data. Do all these Corollas cost the same price? Are they all the same price? No, they're different prices. Why are they different prices? Is it because they're different ages, or is it purely random that they're different prices? R squared tells us how much of that difference in prices we can explain and how much is pure random. 75% of that variability in prices is accounted for by the model. So if someone asks you explain R squared, you fill in this number, just turn that into a percentage, and whatever your units for Y are, you put right there. Just put a word there. The rest of the sentence is the same. Okay, now that we got a model, let's make some predictions. Let's predict the value of a 10-year-old Corolla. 10 years old. Is that an X or a Y? I have to stop and think. Years, was that X or Y? Oh, it's a good thing I wrote that down. X is the age in years. That's an X. So it's literally plug and chug. Plug in X equals 10 into the model. And I get an answer. So the model predicts, remember we start every sentence with the model predicts a 10-year-old Corolla would be worth that amount. And what about 25? Same thing. Plug in X equals 25. And we get this number. And we have to stop and think for a minute. You got a 25-year-old Corolla and your car is so bad that you would have to pay somebody $3,000 to come take it away? Come on, clearly that doesn't make sense. That doesn't mean the model's broken. That just means this model won't work for 25-year-old cars. Remember, we came up with this reasonable domain here, and we just estimated that it probably won't work past 20. We were right in some sense. It clearly doesn't work to 25. So we didn't do anything wrong. It's just the model isn't built to predict the age of 25-year-old Corollas. Okay, what if we ask this question? Now, find me the age of a Corolla that's worth $15,000. In this model, that stands for age. That stands for predicted value, not actual value. These are my actual ages. These are my actual values. I'm using actual ages to predict values. This question wants me to do that backwards. They gave me an actual value. I don't have a y in my formula. I have a y hat. They're asking me to predict an age. I don't see an x hat anywhere. X or hat means predicted. The point of this is you're not allowed to work these models backwards. You're not allowed to plug in for y and solve for x. They're not built for that. If you want to do that, you have to start over from the beginning. Call these your x's, call these your y's, then you could use price to predict age. But this model is not built to do that. This is only built for you plug in an age, it spits out a predicted value. Okay, let's find the residual, find and interpret. That's my favorite phrase, find and interpret. The residual for a particular car, the 7-year-old car, this one right here. So I want to find his residual and interpret that. So that would be this guy right there. So there's his predicted value on the line. There's his actual value. I mean, you can see just from this picture that that car sold at a car lot for less than what the model said it was worth. So residual, you want to write this formula down as actual minus predicted. The actual value, the one from the table, was 10,998. That's what the car lot had it listed at. If I plug 7 into my model, I get this value. Actual minus predicted gives me negative $764. So that's what it was listed for at the lot. That's what the guy actually paid. Or no, so this is what it was worth. So the car sold for $700 below market value. So the buyer got a good deal. So the blue line here, you could think of it like this. The blue line is the Kelley Blue Book value, and the dots are the actual prices. So these cars are being sold for below market value. These up here are being sold for more than market value.